In this video, we are going to talk about analytic functions and mappings of complex variables. In many ways, things will seem familiar because they are similar to things that you've learned for real numbers, because after all, real numbers are a subset of the complex numbers. However, there are things that are different because the complex number is a two-dimensional object. In other words, it has a real component and a y component. So some things will also look different. We will talk about some of those similarities and differences and how we can visualize these analytic functions. We will do examples and look at how we can use our xy coordinates as well as polar coordinates to represent functions. And then we'll talk about mappings in terms of translation, rotation, reflection. We will see that addition of a complex number to another complex number corresponds to translation, whereas if you take a complex number and multiply it by another complex number, that will rotate your vector. And then finally, when you take a complex conjugate, you will get a reflection. So even though a reflection is a special case of rotation, you can get this rotation by taking the complex conjugate. And this is where I have to admit to some hubris, because I had combined several sections of your textbook to get the content for this, and then I thought, yeah, afterwards I'll just do some examples. Well, with all these types of ways of analyzing the mappings, I actually had to break it. This video got hugely long, so I'm going to break it up into two sections. So I talked about what we're going to cover in this video. In the second video, we're going to talk about how to analyze the mappings we have. First, for visualizing functions of a complex variable, it is very much like real numbers, where we picture some number plugging it into a function and getting some other number out. So maybe we plug in z, we get out the number w, which is, we say, equal to f of z. And then z we think of as an xy pair, or z equals x plus iy, and what we get out is a uv pair. In other words, w is equal to u plus iv. It is typical to refer to our domain, or what we plug into the function, as xy, and then our range, or what we get out of the function, as a uv pair. And we talk about the xy plane versus the uv plane. Which brings us to the fact that because the complex numbers are two-dimensional, a function of a complex variable can't be represented well in a two-dimensional plane. So let's just look at this here. So normally, with real numbers, so if x and y are real numbers, then we only need one axis to represent a real number. So in other words, all the real numbers can be represented along the x-axis, and then we can map those x's into y's. So we can say f of x equals y, so we can put the y value after we've plugged in x into y, and then we can have this graph then of x versus y. So we can graph the function on the xy plane. However, because complex numbers are two-dimensional, in other words, we can't just represent a complex number with one axis. We need two axes. We need the x and the y-axis to represent the real and imaginary portion of a complex number. So when we have a function, we can't graph our z versus f of z on a two-dimensional graph. But what we do is we picture it or visualize it by using this mapping kind of look. So we have an xy plane, which represents our domain of our function, and we have a point in the xy plane z, which is equal to the xy coordinate, which is x plus iy. And then we map it with f of z, and so I should put f of z over here. F of z maps z over to a point w in the uv plane, and the uv plane is also considered to be complex. So in other words, w equals uv, which is u plus iv. So this is kind of the way we picture our function, our complex functions, as opposed to just being able to graph it. We have to talk about going from an xy plane to a uv plane. The other useful thing that we do with functions of complex numbers is we often think of breaking up this f of xy that then maps to the uv plane. We think of it as breaking it up into two separate functions, u and v, where u takes x and y and computes the real portion of w, And v takes x and y and computes the imaginary portion of w. And you notice when we do this now, u of xy and vxy are now real valued functions, and you can do everything that you normally do with real valued functions because they are real valued functions. This last idea of taking a function of a complex number and breaking it up into two functions, one that maps to the real portion of your w and another function that maps to the imaginary portion of w, you can do that as well in polar coordinates. So for example, if f of z, now you express z in polar coordinates. So z is equal to r e to the I theta. Here's r, here's theta. It can map that now to z prime, also in the r and theta polar coordinates. So you get a new r prime and a new theta prime. So z prime is equal to r prime, e prime, and theta, not e prime, ei theta prime. Then you can think of this f of z, you can break it up into a function u that maps to the real part of z prime, r theta, and I that maps to the imaginary part of z prime. I've summarized and shrunk down all this information here so that we could look at an example. And the example we will look at is f of z equals z squared. We will start by representing z as x plus iy. And now when we plug it into our function f, we get x plus iy squared using our definition, or just going through and multiplying this out. X plus iy times x plus iy. So you get your x squared here. When you multiply these two, you get minus y squared. Here you get an x iy, and here you also get an x iy. So you have plus I 2xy. Here you can see that the x squared plus y squared is the real portion. So our u of xy is equal to x squared minus y squared. And then here we have v of xy is equal to 2 times xy, which gives us our imaginary portion of f of z. But you'll notice that u and v are now, because they're dealing only with xy's, they're real valued functions. To give a numeric example, let's say z equals 1 plus I. So I've graphed that here. I have 1 on my real axis and 1 on my imaginary axis, so I have 1 plus I right here. When I square it, I can either multiply 1 plus I times 1 plus I. Multiplying here, I get 1. These two multiplied together gives me minus 1. Here I have an I, another I, so I have 2I. Or I could have plugged it into this formula here, and I would have gotten the same thing, which would have been given me the 2I. So over here, on the UV plane, I am going to have 2I. So I'm going to say that f of 1 plus I equals 2I. And again, my function, u of xy is equal to x squared minus y squared. And you see that this u gives us 0 in this case, because x and y are both equal to 1. You see here that v, our imaginary portion, is 2 times x plus y, which is just 2, and that gives us our coordinate in this UV plane. So over here we had used the example of looking at f of z, where z is equal to 1 plus I. So let's do this again in polar coordinates. So we need to convert our 1 plus I to polar coordinates. So our radius is just going to be 1 plus 1 square rooted, so that's the square root of 2. And then our theta, you can see, is pi over 4. Plugging in now our polar representation into f. Using our formula, f of our z is equal to r squared e to the I 2 theta. So I have r squared, which is 2, e to the I, multiplying this by 2 gives us pi over 2. And this is what I have graphically. So I'm representing this point, square root of 2 e to the I pi over 4 gets mapped to 2e to the I pi over 2. And 2e to the pi over 2 you can see is exactly the 2i that we had in our previous work when we were looking at x plus iy representation. Our radius is 2 and our angle is pi over 2. And last, at least for this example, is we can separate out our f of z into a real and imaginary component. So here is our real component, r squared cosine 2 theta, which I rewrote here. And here's our imaginary component, which is r squared sine of 2 theta. And again, this is v and u are both purely real valued functions. It's just that the v then gets multiplied by I, so we refer to v as the imaginary component. The next thing is we'll look at what mappings can do to a vector. They can translate a vector, rotate the vector, or reflect a vector across the real axis. And actually reflection is just a special case of rotation, but we'll single it out as if it's something special. We will start by looking at translation, which corresponds to the addition of a complex number. So if w is equal to f of z, and let's say that w is equal to z plus 1. So if we look at this, break down the z into an x and y component, a real and imaginary component, you'll see that the 1 gets added to the real part, x, and then you have your iy. So what this effectively does is translate each point 1 unit to the right. So here I have a drawing of this. If we have a point z here in the xy plane, and then we transform it by adding 1 to it, that gets 1 is added to the real portion, so we translate z plus 1 gets translated over to the right on the real axis. Whereas if we add something to the imaginary portion, such as w is equal to z plus I, then we have x, the real portion doesn't do anything, but the I portion, we add 1 to it. So it translates each point 1 unit up, and this assumes we're adding. If you subtract, then of course you translate in this. For the y, you translate down, and for x, you translate to the left. But anyway, for this, y plus 1, so if this is our z, our y plus 1 translates it 1 unit up. And you can plug in numbers for z and check this out. And then last, you can add w equals z plus some complex number with a real and imaginary portion, and you'll see that then you have translations both in the along the x-axis or on the x direction, and you combine that with the translation in the y direction. So if we add 1 to the x and 1 to the y, the z component, then we add 1 to the x, add 1 to the y, and we get this z component here, z plus I plus 1. The next thing we want to talk about is rotation, which corresponds to multiplication by a complex number. In particular, multiplication of a complex number by another complex number, r e to the I theta, is a rotation by theta in the clockwise direction. Actually, I should say it includes a rotation because the r does something else. The r is not part of the rotation. It's this e to the I theta that gives you the rotation. We're going to look at this formulaically, and we're going to write everything in exponential form because it's dealing with theta and, a rotation by theta radians. So we have z, a complex number, and if we multiply it times e to the I theta prime, and we chose r equals 1, so we could just isolate what happens with this e to the I theta prime. So we rewrite z in terms of r times e to the I theta, and here is our rotation, e to the I theta prime. So what happens just by properties of exponents, so our r stays, and then we add these angles. So we have e to the I theta plus theta prime. So here is the rotation. We're rotating the vector counterclockwise by theta pi radians. Let's consider f of z is the transform that multiplies a complex number z by I. So in other words, the f of z is equal to z times e to the I pi over 2, since e to the I pi over 2 is equal to I. So what we're saying is that multiplication by I is a counterclockwise rotation by pi over 2. So let's plug in some numbers into z and see what happens. And I have to admit, I had a very specific z in mind to do this with, but let's start with f of 1. So 1 is equal to e to the I 0. So here we are at 1. And then we're going to multiply by e to the I pi over 2. This is just 1, or we can add the exponents, and we get e to the I pi over 2. So what this tells us is if we do this by doing a counterclockwise rotation by pi over 2, what we'd get is this vector here, which is equal to I, which is exactly when we did the algebraic calculation we would get, since e to the I pi over 2 is equal to I. For my next example, I'm going to have f equals -1. And I'm sorry, I'm only going to do easy numbers, easy examples. So here I have -1, right? The radius is 1, and our angle is pi. So this is f of -1 is equal to f of e to the I pi. When I multiply by e to the pi over 2, e to the I pi over 2, by our geometric interpretation, that means we should rotate our 1 vector counterclockwise by pi over 2. And that will give us -I, just geometrically. And then if we do this algebraically, you can see we'll have e to the 3 pi, e to the I 3 pi over 2, which is equal to -1. Now I have this last example here, which I specifically wanted to do. So f of I. So now we have f of e to the I pi over 2. And I have this written, here's f of I, right? 1 in the positive, radius 1 in the positive I direction. So when we plug it into I times z, this is e to the I pi over 2 squared. So this is I squared. And if I do this geometrically, I rotate this by pi over 2, and I get -1. I need a negative here. So I have a -1. I do this algebraically, and I get e to the I pi, which is equal to -1. So here you have, in complex numbers, you have the fact that I squared is equal to -1. The last thing on our list is reflections, which corresponds to taking the complex conjugate. So if W is the complex conjugate of Z, if Z is equal to x plus IY, then W will equal to x minus IY, and it reflects across the real axis. So if this is our Z, it's equal to XY, then W is equal to the complex conjugate, which is equal to x minus y, and you can see how it reflects across the real axis. At this point, I'm going to say when we analyze mappings, there are different approaches that I sort of boiled down to 3 different things. First, we can convert to polar and then analyze translations, rotations, reflections. And I will do one example of this in this video. Then the other thing we can do, which I'll do in my other video, is we can have z, and as I said, we could represent that as the u of xy plus I of vxy, and then we can analyze this transformation by looking at what happens when we hold u of xy constant, seeing what happens to the translation. Then we can also look at v of xy held constant. That gives us sort of some indication, sort of like when we had vector calculus, we used to look at level curves. And the analogy is kind of appropriate because we did this in vector calculus because we had these multi-dimensions, which is exactly what we have now with functions of complex variables because we're going from 2 dimensions to 2 dimensions. Last, we often analyze regions, often rectangular regions in the xy plane to see what happens. And this is also something we will do in the next video. But first we'll do one example of this since we have talked about translations, rotations, and reflections. Here's the function f of z equals z squared. And the first thing I'm going to do is write my z in terms of x plus iy, and then I'm going to plug it into my function x plus iy squared, which gives me x squared minus y squared plus I times 2xy, where I can separate this out into my u of xy, which gives me the real portion, and my v of xy, which multiplies by I to give me my imaginary portion. And I do this almost out of habit. But before we use this to do an analysis, I want to do a different type of analysis where we have the polar coordinates, w equals f, and now we express z as r e to the I theta, plugging into our function, that's r e to the I theta squared, which is equal to r squared e to the I 2 theta. I'll expand this step out just to remind you how I get from here to here. So r e to the I theta squared is equal to r e to the I theta times r e to the I theta. And by our earlier discussion of different transformations, rotation was one of them. And we said multiplication by a complex number, z e to the I theta prime. So we multiply a z by e to the I theta prime. That rotates z counterclockwise by theta prime And what we ended up doing is we added our thetas. So that's exactly what I did here. I have z, and I'm multiplying by r e to the I theta, so I have to add the thetas, so I get my 2 theta here. And continuing on, so just to kind of remind myself, so far what happens to w, it squares the radius, and it doubles the angle theta. We go from theta to 2 theta. And I also wrote this out using Euler's identity. This is r squared cosine 2 theta plus I sine of 2 theta. So let's look at this. W squares the radius and doubles the angle. So squaring the radius means points on the circle z equals r naught e to the I theta with radius r naught are now mapped onto a circle of radius r naught squared. The doubling of the angle now means that the circle is traversed twice as fast. So what does that mean? So let's look at just this little arc here. Originally, we have a radius of r naught. And if we can just consider the arc from theta equals 0 to pi over 2, now that's going to map into a circle of radius r naught squared. I should actually have written r naught squared instead of r naught prime. But just know that r naught prime is equal to r naught squared. And when I say twice as fast, so now we've covered, instead of just covering 0 to pi over 2, we cover 0 to pi, so twice as much area. So the arc in the first quadrant is mapped to this arc in the upper half of the plane. You can also imagine now, if we go from half the arc, we're going twice as fast. So if we just map the top half of the arc, after we have our transformation, we're going to have the complete circle. And then again, if we traverse the circle once over here in this original domain, for after our transformation, we will have traversed the circle twice. So this is what I mean as twice as fast. And the last thing to note is this map is not one-to-one. You kind of get that feeling because you're traversing it twice as fast. And we can show this specifically by showing that there are 2 numbers over here in this domain that maps to the same number in the range. So w r naught e to the 0, so over here, r naught, is equal to r naught squared, e to the 2 times 0, which is just r naught squared. Whereas w r naught e to the I pi, that's over here on this side, is equal to r naught squared e to the I 2 pi. And so now we've come back all the way around at r naught squared. So this mapping is not one-to-one, since essentially it maps positive and negative real axis are mapped into the positive axis. As we see in this example where we have something positive versus something negative, and both of them get mapped to the positive r naught squared. At this point, this is where we will stop, and we will have a second part of this video. So that's it for this video. Thank you for watching.